There's a company in the Netherlands that every government on Earth is watching right now, and most people have never heard of it. It doesn't make smartphones or GPUs or AI chips. It makes the machines that make the machines, and it is, without exaggeration, one of the most strategically important companies on the planet. I'm talking about ASML, and right now, for the first time in decades, they're scared. Now, to understand why the fear, you need to understand what ASML actually does, and it starts with light. When chip makers build a processor, they're essentially printing incredibly tiny patterns onto silicon. Transistors, wires, logic gates, all of it stacked and etched in layers. The way they do it is called lithography, which is basically photography at an insane scale. You shine light through a pattern mask onto a silicon wafer coated with a light-sensitive material, and whenever the light hits, the material changes. That lets engineers etch away certain parts and build up others. The problem, however, is physics. Light behaves like a wave, and waves can only resolve features down to roughly the size of their own wavelength. So if your light has a wavelength of, say, 193 nanometers, which is what older machines use, you can't reliably print features smaller than that without tricks, and today's chips need features at 3 nanometers, 2 nanometers, and they're still heading lower. The solution ASML cracked after literally decades of works and billions of dollars poured into it was extreme ultraviolet light, or EUV for short. EUV has a wavelength of just 13.5 nanometers, and to generate it, they fire 2 high-powered CO2 lasers at a tiny tin droplet 50,000 times per second, creating a plasma hotter than surface of the sun, which releases that precious 13.5 nanometer light. The whole thing has to happen in a near-perfect vacuum because UV photons get absorbed by literally everything, including air. Instead of glass lenses, the light gets guided by mirrors coated with alternating layers of molybdenum and silicon, each layer only a few nanometers thick, polished to precision that is genuinely mind-bending. Carl Zeiss in Germany makes these mirrors exclusively for ASML, and they don't sell them to anyone else. This is why no one has replicated it. It's not one breakthrough, it's thousands of them stacked on top of each other, protected by a network of 5,000 suppliers that are all essentially locked into ASML's ecosystem. The moat is real and it's enormous, but now there are two groups of people who think they can build something better, or build something parallel. I think that's more precise. And both paths lead to the same destination. ASML loses its monopoly. Now, let's start with the American bet, and that's xLight. And let me introduce you to xLight. Palo Ultra startup founded quietly, and then in early 2025, they made headlines by bringing on Pat Gelsinger as executive chairman. You probably know Gelsinger as the guy who spent 4 years trying to turn Intel around, didn't quite get there, and stepped down in late 2024. Controversial tenure, sure, but the man knows semiconductors at a level very few people on Earth do, so when he shows up at a chip startup, people definitely pay attention. xLight is not trying to build an EUV scanner. They're not going head-to-head with ASML's full machine. What they're targeting is the light source, the heart of the whole system, the part that generates the UV photons in the first place, and the technology they're using is, well, it's genuinely wild. They're building free-electron lasers powered by particle accelerators. Now, that's the kind of thing that lives at a CERN and takes up kilometers of tunnels. xLight wants to miniaturize that concept, and I use miniaturize loosely here because their planned systems are about 100 meters by 50 meters, roughly the size of a football field. And the idea is to install them outside chip fabrication plants as a utility-scale light source. One of these systems could potentially power multiple lithography scanners inside the fab at the same time, rather than each machine needing its own dedicated plasma source. Now, the physics here are genuinely compelling. A free electron laser doesn't need tin droplets or plasma. Electrons get accelerated to near light speed and then pushed through a magnetic field called an undulator, which causes them to oscillate and emit extremely intense coherent light. You can tune the wavelength. You can push it down to 2 nanometers compared to ASML's 13.5 nanometers today. That is a massive potential leap in resolution, and because there's no messy tin plasma involved, the light is brighter, spectrally narrower, and more stable. xLight says this could cut EUV costs by 50% and boost fab productivity by 30 to 40%. Their own website claims deployment across existing fabs could increase manufacturing productivity by 50%, and that is definitely not a minor tweak. That's potentially transformative economics for the whole industry. In December 2025, the Trump administration signed a letter of intent to provide up to $150 million in CHIPS Act funding to make this real. The government gets an equity stake in return, potentially becoming xLight's largest shareholder. The plan is to build and demonstrate a free electron laser prototype at the Albany Nanotech Complex in New York, with first test wafers targeted for 2028. Gelsinger put it plainly, "We're here to wake up Moore's Law. It's been taking a nap." I personally find this exciting, and I say that as someone who follows this space pretty closely. This isn't vaporwave from a random startup. The CEO, Nicholas Kellett, spent 2 decades building large-scale X-ray science facilities at national labs like the SLAC and Lawrence Berkeley. He was chief engineer for the LINAC coherent light source. These people have actually built particle accelerator-based light sources before, and the jump from national lab to semiconductor fab is still enormous, but the underlying physics is proven. Worth noting too, ASML actually tried a similar approach about a decade ago and walked away because the technology wasn't mature enough. Kellett addressed this directly and argues the key enabling technologies have since caught up. The question is whether 2028 is realistic or if it is just an optimistic fundraiser talk. I think it's probably somewhere in between, and that's still worth getting excited about. Now, here's where things get geopolitically intense, because while xLight is building towards 2028, something else was already happening quietly in a high-security lab in Shenzhen, and Reuters broke the story in December 2025. China has built a functional prototype EUV machine, not a production-ready system, not something that can churn out 2 nanometers at high volume, but a working prototype that can generate EUV light at 13.5 nanometers, the same wavelength ASML uses. This is the first time any country outside the Netherlands have independently pulled this off. The backstory is remarkable. Since 2018, the US pressured the Netherlands to block EUV sales to China. Not a single ASML EUV machine has ever been delivered there. The whole strategy was to cut off access to leading-edge lithography and keep China at least 1 generation behind. What actually happened is that China treated it as an existential threat and responded accordingly. Beijing designated chip independence as a national security priority, funded it with the equivalent of $37 billion investment fund, and started recruiting aggressively. Former ASML engineers were headhunted starting in 2019, and some allegedly under false identities, working in closed facilities with tight security. Inside Huawei, semiconductor teams reportedly work in isolated units, with some engineers sleeping on site and operating with a limited outside communication. One source described the internal setup as a separation by design. The Shenzhen prototype uses laser-inducted discharge plasma approach instead of ASML's laser-produced plasma method. Rather than firing lasers at tin droplets, the system vaporizes tin between electrodes using high-voltage discharge. It is a potentially simpler and cheaper method, though it currently runs at much lower power output, somewhere around 50 to 100 watts compared to ASML's significantly higher levels. And on a parallel track, there's an even more ambitious project. Tsinghua University is working on something called steady-state micro-bunching, or SSMB, which, like xLight, uses a particle accelerator to generate UV light. Their approach aims for a continuous, stable beam rather than pulsed light, theoretically heating 1 kilowatt or higher of EUV power. If this actually works, it could leapfrog ASML's current high-NA EUV systems entirely. The biggest remaining wall for China is optics. ASML's mirrors made by Carl Zeiss are so precisely polished that if you scale one up to the size of the Earth, the surface deviation would be smaller than the width of a human hair. China's Changchun Institute of Optics has been making progress, but matching the precision and keeping it consistent under 24/7 industrial radiation exposure is a completely different challenge. The government's official target is chip production by 2028, but Reuters sources say 2030 is more realistic. Still, the fact that this prototype exists at all is, well, it's significant. ASML's own CEO said China would need many years, and that gap is, well, clearly closing faster than most people predicted. So let's zoom out, because I think just saying ASML is threatened misses the bigger picture. There are now 3 simultaneous pressures hitting the world's most important technology monopoly at once. You've got xLight chasing a fundamentally better light source from inside the American innovation ecosystem, backed by federal money and some serious semiconductor experience. You've got China treating chip independence like a survival mission with state resources that are basically unlimited and a prototype that already exists. And ASML itself is responding by pushing EUV power towards 1000 watts, rolling out high NA systems for sub-2 nanometer chips, and branching out into packaging tools for the AI era. Now, what makes this moment genuinely historic is that both economic and geopolitical pressure are converging at the same time. Historically, ASML could count on 2 things. Nobody had the resources or the institutional knowledge to replicate what they'd build, and every major chip maker needed them so badly that nobody was seriously motivated to look for alternatives. Both of these assumptions are now being stress tested simultaneously. Now, my honest take is that xLight is more technically credible near-term disruption to how the EUV ecosystem works. Not because it will replace ASML outright, but because if they can actually deliver a free-electron laser light source that plugs into existing ASML scanners and cuts costs by 30 to 50%, the whole dynamic will shift. ASML goes from being a close to replaceable system to being more of a platform, and that is a big deal. China's path is harder and longer, no question, but getting to a working prototype faster than Western analytics expected, that's a signal worth taking seriously, not brushing off. The semiconductor industry is entering an era of real competition for the first time in decades, and honestly, I think this is a good thing. Monopolies don't push boundaries under pressure, they just hold their ground. Competition is what forces actual breakthroughs, and right now the pressure on ASML is higher than it's ever been in history. So, where do you think this goes? Is xLight actually going to deliver by 2028, or is that timeline more wishful thinking than engineering reality? And does China's prototype genuinely shift the calculus of the chip war? Let me know below, because I read every comment. Until then, don't forget to subscribe to the channel and hit the thumbs up if you like the video.